Hello and welcome back to Real Analysis. And first I want to thank all the nice supporters on Steady or PayPal. In today's part 15 we will talk about infinite sums, also called series. Indeed, this is such an important topic that we will use the next videos to talk about all the details. Here we just start how we can define such an infinite sum in a rigorous way. And in the end you will see this is not so new, a series is just a special sequence. And how you can deal with sequences you have already learned here. Okay, now in some problems it can occur that we need to add up infinitely many numbers. For example, we have the number a1, then we add a2, then a3, a4 and so on. To make this shorter you could say let's use the sum symbol, the capital sigma, where we go from k is equal to 1 to infinity. This is then what we call a series, so just adding infinitely many numbers. So you see, this is not so complicated, so let's immediately look at an example. The only thing we need here is a sequence ak of real numbers. Therefore let's take one we already know, which is -1 to the power k. So this is a well-defined sequence, however not a convergent one. Nevertheless, we still could ask what is the infinite sum of this sequence. Here we know we start with -1 and then we add 1. And then afterwards we add -1 again. And then 1 again, then -1 again and so on. Of course, this is what we can easily calculate because we can set parentheses here, and then we see we just add zeros. Hence the result of this infinite sum should be 0 as well. Okay, at this point you should ask, why do we set the parentheses in this way? Of course there are also other possible ways. For example, we could skip the first element -1 and set the parentheses here. Then we still add zeros, but what remains is -1. Okay, now we have two different possible results. So we immediately see such infinite sums here make problems. So we need to define them and they don't act like normal sums at all. Because in a normal sum we can set the parentheses as we want. And at the moment we don't know in which cases we are allowed to do this for an infinite sum as well. This might be a little bit confusing because we use the same symbol, but we could have different calculation rules. Therefore first let's define the symbol in a mathematical way. So this will be our definition of a series. For this let ak be any sequence of real numbers. And then we define a new sequence Sn by setting Sn to be the sum of the first n members of the sequence ak. So this is just a normal finite sum. Hence Sn is a real number as well. Therefore the whole sequence given by Sn is what we call the series. And now you should see, in the case that this sequence is convergent, we have a meaning for the infinite sum. Therefore we are also able to define the symbol where we have infinity at the sum here. So this is simply the limit n to infinity of Sn. Or without using a new name, you simply would say it's the limit of these partial sums. Okay, there we have the case that often leads to confusion. Namely, this symbol here is frequently used in two different meanings. On the one hand, you can use it for the whole sequence Sn, because then you don't need to introduce a new name. And on the other hand, it's also used for the limit if it exists. Therefore, please be careful, sometimes you are allowed to calculate with the symbol as a number, but other times such a calculation can lead to contradictions. Okay, so that's the definition and the introduction for a series, and in the next video I will show you an example, namely the important geometric series. Hence a good transition would be to rewrite our example from above. Let's formulate this into the sequence of partial sums. There ak is -1 to the power k. Now let's write the sum here as a sequence with index n. There, for calculating the first member, we put in the index n is equal to 1 and get out -1. Then for the next member, we have n is equal to 2, which means we have -1 plus 1 and we get 0. And then for n is equal to 3, we get -1 again. Then this simply repeats with this pattern. And here you know, this sequence is not convergent. Okay, maybe for closing this video, also another example would be helpful. Okay, here I want to ask the question, what happens when we put in +1 instead of -1? Of course, then the power k does not matter at all, because we always get out 1. Therefore, for our sequence of partial sums, we get out 1, then 2, then 3, and so on. Obviously, this is also a sequence that is not convergent. However, we could say it's divergent to infinity. Now, I already told you that in the next video we will talk about the geometric series. This will generalize these two examples, but then we will also get convergent series. Therefore, I hope I see you there and have a nice day. Bye!